Hello, today we are going to go over the influence of the symmetry on the magnetic properties of the metals. So in this case, we look on the transition metals. So before we looked at the properties of the transition metals, and we saw that there is such so-called Stoner criteria, which says that multiplication of U, which is integral, will be given with the integral, and the number of states at Fermi level should be larger than 1. So this is criteria for the magnetic properties. In this case, it corresponds to the ferromagnetic metals, transition metals. We know that among them there are cobalt, iron, and nickel. They have these properties that are described in with this equation. So, and we can look at the properties of some other elements, for example, 4D and 5D, and in one picture, before we saw that among 4D and 5D elements, there is palladium and platinum that could show good properties. The Stoner criteria is very close to 1. So there is, if we change the dimensionality of the systems, there could be some chances to increase this number of states at Fermi level. So this number of states at Fermi level should be larger than 1 over U, and it corresponds to that if we increase this number of states, then there will be a good chance to get the Stoner criteria working. So we have here two-dimensional, one-dimensional, and zero-dimensional case. In case of two-dimensional case, we have here this curve. It describes number of states per atom. And as we decrease the dimensionality, we can see that in 1D case, we have this large value of number of states. And for zero dimension, in this case, it corresponds to isolated atom, or we call it other atom. In this case, we have number of states, just peaking and looking as a delta function. So, and this corresponds to the good chance that Stoner criteria will work. Now, let's. There were some density functional theory calculations, and these density functional calculations, theory calculations show that this is correct to some value. So, for example, in this case, we have these calculations performed, and the magnetic moments of the isolated atoms and the atoms in the bulk were measured with this program. So here we have open squares. These open squares correspond to the atoms of 3D elements. For example, we have here titan, vanadium, chrome, manganese, iron, cobalt, and nickel. And in the case of chrome and manganese, we have some maximum values of the magnetic moment here for isolated atoms. And if you consider bulk atoms, atoms in the bulk, so this curve corresponds to the atoms in the bulk. So we have here this theory that with decreasing of dimensionality, the number of states increases, and number of states could increase only because if you have magnetic moments, larger values of the magnetic moments corresponding to the isolated atoms here. And we have here this other experiment. In this experiment, there were performed again density functional theory calculations, and they calculated values of the magnetic moments in the clusters. So we have here clusters on the x-axis, and there's a number of atoms in the clusters. So as we decrease number of atoms in the clusters, at some value equal to about at 400 for nickel, we will have change in magnetic moment, and this change in the magnetic moment correspond to the magnetic moment in the for one atom in the cluster. So as we decrease the number of atoms in the cluster, this magnetic moment increases, and we will have at some value it just corresponds. It gives us value. It gets very close to the value of the magnetic momentum of one isolated atom. So for cobalt case we have this picture, and for cobalt picture for cobalt we have same thing. So number of states, number of atoms in the cluster decreases, and at some value we have now increase in the magnetic moment. So these two density DFT calculations show that with decreasing of dimensionality we will have increase in number of states at Fermi level, and this corresponds to the good changes of Stoner criteria working. Now let us look at this picture. In this picture we have Stoner criteria. So Stoner criteria is described as U times N EF, which is number of states at Fermi level. So this value of 1 corresponds to the to this limiting case, and from this picture we can see that there are 3 elements, 3D elements. Among them is iron, cobalt, and nickel. That they have these points. They have large values of the Stoner criteria, and they will have good. They show very good magnetic properties. They are ferromagnets. And if we look at the 4D and 5D, in this case, among them 4D and 5D is platinum and palladium. So they will have larger values. Values of the Stoner criteria very close to 1. So these big points correspond to this platinum, and this one is to palladium. So if so, there will be a chance to get very good magnetic properties from them if we change the dimensionality. But it appears that it depends on some other cases. So, for example, in this experiment that was performed with density functional theory, they were done for 4D and 5D elements here, and it showed again this magnetic moment on the y-axis here, and on the axis we have different atoms of 4D and 5D elements. So, for example, this is the case for 4D elements. We will have this picture here, and only for the case of molybdenum we will have large magnetic moment corresponding to the odd atom. So odd atom, this odd atom was created on the surface of the silver. Whereas in the case of palladium platinum, these magnetic moments are equal to 0. So this doesn't add up because we already said that the palladium among 4D and 5D, only palladium and the platinum could have better chances for Stoner criteria. So it appears that it depends on the overlap of number of states of these 4D and 5D elements, and with the number of states of bulk material that we are putting on. For example, in this case, for the case of palladium and platinum, number of states for palladium and platinum do not coincide with number of states of silver. And for this material, we have molybdenum on the silver. It shows that number of states of molybdenum per atom. They will would correspond overlap with number of states in silver. So this could be shown with the picture here, and this picture here is described with this one. So, for example, we have here this 5 cobalt atom, and we put cobalt atom cobalt add atom on the subsequently on some elements, bulk material formed by the 4D elements. So for example, here we have rhodium, and this picture here is the silver. So in the case of rhodium, of cobalt on rhodium, so this line corresponds to the number of states of cobalt. So this number of states of cobalt, they will have smaller values of the bandwidth, but increased value of number of states. Whereas for the 3D, three-dimensional rhodium, this will have larger values of bandwidth, but larger value of bandwidth, but smaller value of the number of states on y-axis. And this corresponds to the case that they overlap. So if we prepare this cobalt on rhodium, there are good chances that there will be good magnetic properties of this cobalt atom. Now, in this picture, we have, in the second picture, we have here this cobalt on silver, and in this case, we will have the case that this number of states do not overlap. So this is, as usual, our number of states of cobalt atom, and the number of states of silver, three-dimensional, is only here. So we will have here this that they do not overlap, and this corresponds to the case that cobalt on silver doesn't show very good magnetic properties here. So it depends not only on the Stern criteria, it also depends on this overlap of number of states of this bulk material and this atom. So there are other cases that we can have here that increased values of the magnetic properties, and this corresponds to the change or control of magnetic properties by the voltage gate, by gate voltage. So here, this is accomplished by this experiment. By this experiment was shown that if we prepare some electrodes with platinum and we do deposition on some ionic liquid on them, and we will have this increased values of the number of electrons. And again, it's shown by the experiments on the whole conductivity. In this case, we have that increased values of the magnetic properties, and this corresponds to anomalous Hall effect. And this anomalous Hall effect shows that these elements or this platinum material shows good, very good magnetic properties. So at this experiment, we conclude our lecture here.